Good morning, everyone. We're just going to wait until everyone has joined our webinar as participants, and then give a brief introduction and we'll dive into the presentations. Morning to everyone who just joined us. So we're just waiting till numbers are stabilizing of people joining, and then we'll kick off with our presentations. Great. The number of people that are joining us is slowing down a little bit, so I suggest we kick off. So good morning, everyone, and thank you very much for joining us for our webinar on space-based solar power enablers. My name is Frank Schoos. I'm a space energy development engineer at Catapult, and I was the technical lead for the project. So I will be hosting and walking you through the different presentations today. First off, though, I would like to just a few housekeeping rules. Any questions, if you put those in the Q&A tab somewhere here at the bottom of your screen, and we'll pick those up at the end of all the presentations, and we'll try to address as many as possible. If you do have any questions that have not been addressed or anything afterwards, please don't hesitate to get in touch either with me or any of the participants if they share their contact details, and we can pick this up afterwards. To start us off, I would like to introduce Mamata from UK Space Agency, who will give the Space Agency perspective on space-based solar power. So, Mamata, all yours.
Thank you, Frank. I'll just start sharing the screen. Let me know if you can see it.
Yeah.
Okay, good. A very good morning to everyone. I'm Mamata Maheshwarappa. I'm the Payload Systems Lead within the Office of Chief Engineer at UK Space Agency. For those who are not aware, we now have a technical team, which is led by our Chief Engineer, Andrew Ratcliffe, and we have 4 different streams within the Office of the Chief Engineer. We have space, mission, launch, and payload. I lead the payload stream, where I provide technical assurance and have an oversight on national instruments that go on NASA, ESA, and other bilateral missions. And I'm also the technical lead on the space-based solar power initiative from UK Space Agency. Space-based solar power almost needs no introduction. Firstly, considering the attention it has been receiving in the recent months and years, and has started to be taken seriously than ever before. Secondly, considering the audience here who are involved in this journey in one way or the other, or have a great interest or passion in the topic. Therefore, I thought instead of dwelling into the details of the concept itself, which I'm sure other speakers will do later in this call, I'll highlight the importance and why we at UK Space Agency are interested and talk about the initiatives and their status. So some of the driving factors for a new form of renewable energy are that on one side, we have the demand for energy, which is increasing day by day with the modern lifestyle. And still there are around 2 billion people who have no access to the electricity. And this demand is only going to increase, and it is expected to increase by two-folds by 2050 with the increasing population. On the other hand, the recent events around the world have raised concerns over energy security and, most importantly, climate change, with the raising fossil fuel-driven greenhouse gases. And if we were to achieve carbon neutrality, the studies suggest that almost 90% of these energies must be from renewable or nuclear sources. So one of the potential solutions is space-based solar power. This was first described by Peter Glaser in 1968 and patented in 1973, basically to collect solar power in space using photovoltaic cells and transmit it back to Earth using either microwave or laser beam, which could then be connected to national grids. Since then, there have been several concepts, such as multi-rotary joint solar powered satellite SPS from China, SPS Alpha from US, and there is our own concept called Cassiopeia, which you see on the screen, developed by Ian Cash here in the UK. We do use some of the solar energy on Earth, which produces less than 1/10 of 1% of the energy we currently use, that is producing 20 gigawatts of power. Even if we were to scale it up, there are challenges due to reduced solar flux that reaches Earth, which is quarter of what we receive in Earth's orbit. Harnessing the power 24 hours a day is a challenge, as the solar power remains attenuated due to cloud, weather conditions, different variant of latitudes, and interrupted by day and night cycles. So these challenges could be mitigated by having the solar power satellite in higher Earth orbit, preferably in geosynchronous orbits. Then why have we not already done it? Spoiler alert, there are more challenges. So I'll go into these challenges in a minute, but the image in the bottom right corner gives the sense of the magnitude and complexity of the structure we are thinking of building in space, which is bigger than anything we have on Earth, let alone in space. So why now? While scientists and engineers around the world have recognized the potential of space-based solar power for decades, the cost implications have meant that it was not economically feasible. But now, thanks to low-cost commercial space launch vehicles, such as Elon Musk's SpaceX program, and rapid advances in the lightweight solar panels, wireless power transmission technology, and the budget could now be within reach. And also having robotics can eliminate the need of having humans to build the structure in space, which again helps in bringing the cost down. So as I mentioned earlier, there are many challenges that we need to address. To mention a few, very top level ones, not going into the technical challenges yet. Firstly, we need to understand the complexity of launching and building the biggest ever structure in space, and that too using robots and AI. We are still yet understanding the debris mitigation and end-of-life measures for the existing satellites in space, and this definitely needs to be sped up if we were to have SPSP. We need to understand the volume of the launches required, probably around the world, and the regulations and the licenses associated with that. The effect of flora and fauna is not understood yet. We need to go into the details of that as well. And the challenges with the frequency spectrum and the interferences caused to the existing infrastructure, etc. I'm very sure this topic is covered later, so I'm keen to hear on that. So in order to address some of these challenges mentioned, we in the UK have got several initiatives. The first one being the technical feasibility study performed by then BEIS, which is now Department of Energy Security and Net Zero. This work was led by Fraser Nash and completed in 2021. Following this, we have a UKSA Department of Energy Net Zero joint SPSP innovation call with 4 different lots focusing on different aspects. Such as in lot 1, we have wireless power transmission. Lot 2 has high concentration solar photovoltaic cells. Lot 3 focusing on systems energy and energy engineering. And we at UK Space Agency are focusing on lot 4, which is looking at mission architecture feasibility study. I guess there'll be some announcements around next week in Bristol, so stay tuned on that. So while this was all being set up, we supported Satellite Catapult in investigating program enablers and accelerators that has now been completed and which is going through review. I've read some reports already, and there is some great work that has gone into it, but also more challenges being identified. I'm sure we'll hear more about the findings during the webinar, which is good. That's how we learn about the complexities. So there are all these national activities, but internationally, this has raised interest in countries such as Saudi Arabia, who have ambitious plans for collaboration and innovation, and also European Space Agency, who are exploring the feasibility of space-based solar power through Solaris program. Lastly, what I would like to say with all these initiatives and the momentum building in the world, in the UK and around the world, is that if we are successful, we will not only just start a business, but launch an industry. But none of that is possible without your support and hard work. So thank you.
Great. Thank you very much, Mamatha, for that introduction. I will just introduce our catapult perspective then on that before we go into the details. I'm just finding the right screen to share. Great. So, right. So, as I already said at the beginning of the call, my name is Frank Schoofs. I'm a Space Energy Development Engineer at Catapult, and I'm technical lead for the Space and Solar Power Enablers work. And I will just introduce how we got there, what the overview of the program is, and then we can go into the details of the different tasks. So first of all, the mission of the Catapult is to innovate for a better world empowered by space. And the way we do that at the Satellite Applications Catapult is within our strategic framework, we're covering different themes and missions around autonomous Earth, connected Earth, beyond Earth, and then where space-based solar power fits is sustainable Earth. We've got various different ways in which we try to live up to our mission by working with the marketplace, enabling businesses, and empowering technology and looking at those to cutting-edge technology. So in Sustainable Earth, so these missions are portfolios of different projects and themes that try to achieve a certain goal. And so in Sustainable Earth, that's where the space-based solar power program sits as what we call an intervention or a strategic theme. And so the Catapult has different activities in space-based solar power fitting within the framework that Mamatha just described. So the first activity is around the Space Energy Initiative. So Catapult was one of the co-founders of the Space Energy Initiative. And then we are also supporting Space Solar, which was set up based on the recommendation of the advisory board to the Space Energy Initiative in order to attract funding for the program. Other activities that we are working on, we are working on a Phase 0 Phase A study with Halasselina Space as our partner, which is funded by the SBSP Innovation Competition, which Mamatha mentioned. This is the Lot 4 aspect. We also have a project in Lot 1 around wireless power transmission, working with Imperial College and Queen's University Belfast. And so in both cases, we are looking at the Cassiopeia concept and trying to work with that to try and build more confidence in the final solution based on the Cassiopeia architecture. And then the final strand is the SBSP enablers work, which of course we're talking about today. Just want to come back to the Space Energy Initiative. So as part of the Space Energy Initiative, we developed a roadmap to delivery of space-based solar power. It's broken down in different phases, in 4 phases, with key demonstrators in each phase of increasing complexity, increasing power delivery, but mimicking our learning along the way, and the technology risk reduction, because again, Mamatha introduced different risks alongside that go alongside space-based solar power. Rather than trying to tackle all of them at once, we're looking at a progressive de-risking activity across 12 years. Now, 12 years is very tight. which is why we worked with the Space Agency to define our Enablers project. And there are three principal aims for that project. The first one is to try and increase our confidence in and enabling the rapid development of space-based solar power. So we've got that ambitious plan. How can we increase our confidence that we can achieve that, and how can we make sure that we maintain the pace of that? The second major aim of the Enablers project is to confirm the UK's position as a frontrunner in realizing space-based solar power. And it's been amazing to see the attention and the applause for the SEI, and we're really building on that within this project. And finally, we want to leverage crossover benefits wherever possible, and that's going from the space-based solar power program to other sectors or other applications, but also bringing in learnings from other industries where possible. So with these aims, we then looked at defining the scope. What are the key questions that we try to answer? So the first question is, what knowledge can we leverage to accelerate the program? Is there anyone else out there who's trying to do something similar or not quite similar but relevant to our program? Second question is, how can we increase our confidence in wireless power transmission and work with that? Third question is, how can we rapidly test robotic manipulator prototypes? So we don't yet know necessarily what those manipulators would look like, what those robots would need to do, what they look like, what we need to test, but we need to be able to rapidly test those prototypes in order to screen them. So that's what we're figuring out with this question. And then the final question is, how can we address concerns around infrastructure and security? Again, one of the challenges that Mamad has touched upon. So those four questions led to a project structure based on those four key themes with different tasks between them. So we looked at digital engineering, standards, regulation in order to fast track in-orbit demonstrators. Around power transmission, we looked at a pre-phase A study for a vertical demonstrator that we proposed within the SEI roadmap. We looked at modeling, interference, there's a robotics piece, and then around infrastructure and security, we looked at cybersecurity and mission security, and also an early assessment of potential biodiversity impact. Now, of course, this is very ambitious. This is not something that Satellite Applications Catapult can do on its own, and we really built on the strength of the SEI and the supply chain within the UK to help us deliver this program and provide us with expert input. And so you can see the logos of the different organizations that worked on this, and we've got all those experts here today to talk briefly about their work that they've done on this project. So we'll now get into the juicy bit of the technical details. So we're going to just follow and run through them, and we get people to share their key findings with you today. So the first person and the first organization is Accenture. So I'm going to stop sharing. And Sonia is going to talk us through Accenture's findings on digital engineering. And Harriet is going to support her later on with the Q&A as well.
Thank you, Frank. Hello, everyone. Thank you for having me on this call. I'm a senior manager within Accenture's power generation and infrastructure practice, and I'd be leading the Accenture team who've been working alongside Frank, Dave, and the Catapult team to deliver or define a digital engineering roadmap that will enable the space-based solar power program. And this has been part of the enablers workstream that Frank, you just talked to. I also have Harriet here, who's joining me, and she's our digital engineering specialist, and she'll be also partnering with me on this segment to give a bit of an overview of what we have been delivering. If we jump to the next slide. So in February this year, we kicked off a piece of work with the Space-Based Solar Power Programme to better understand what digital engineering capabilities are required to design and develop a first-of-a-kind space solar system that we've just heard about. So we know that digital, it's well understood that it's a crucial enabler to any major capital project delivery, particularly in the energy sector. Our research shows that 9 out of 10 major projects have cost overruns and more than 90% are not delivered to schedule. So digital is a really key lever in enabling capital projects to be delivered on time and to cost, and even more important when we're thinking about targets that have been set from a net zero perspective. We need space-based solar power for baseload electricity to help achieve that 2050 target. So we are working to tight timescales, and we need to prove and build out these assets and this baseload electricity fast to keep that goal alive. So being greenfield projects, space-based solar power has a real opportunity to begin with really good digital practices to begin with. But there are some challenges that many typical heritage projects and old organisations tend to struggle with, that actually space-based solar power could really overcome from the outset. Heritage projects tend to have significant and rising IT regret costs, a significant systems obsolescence, and a wide range of challenges when it comes to having the right capabilities to actually compete effectively. So one of these challenges also that we see from some of these organisations is actually having sufficient access, and unvetted access, but also structured access to data, and data that really is built up over the life cycle of the projects, from engineering design through to operational data, and having those practices and those capabilities set out from the beginning is really going to help to support the digital engineering journey for the space-based solar power programme. So the projects that we initiated along with Frank and the team was very much exploratory. It was very much centered around a number of co-creation workshops to scope out what capabilities are required from a digital engineering perspective. There are unique characteristics to this programme, as we've heard about. The project is unique, it's at an early stage, which also means that there are a number of unknowns that we need to factor into defining the capabilities and maturing them over time. There's also a variety of specific characteristics that we need to take into account. So things like, as we popped up on the slide, the aspects around hypermodularity of the system, the creation of a disaggregated system of systems, the necessity for remote O&M, and so forth. We also need to take into account how the asset will be designed and delivered, and there's unique characteristics pertaining to that as well. So there'll be a necessity for a high volume of manufacturing of components and materials, a concurrent level of design, so concept design, there'll be multiple concept design that will be established, and and multiple designs that will be worked through in parallel. But there's also a need for the enabling infrastructure to support this. So it's both a manufacturing engineering challenge, but also there'll be a capital project aspect to this as well that I mentioned. So if we jump to the next slide, before I hand over to Harriet to explain what we delivered and some of the outputs that we pulled together with the team, I just wanted to give you a flavour of what is the ambition of this piece of work, and some of the design principles that will help us structure and focus the decisions around what digital tooling what digital tools do we invest in going forward. So in terms of the ambition, this is very clear. The programme is a complex, first of a kind, and accelerated programme, which is critical to net zero, as I've just mentioned. But to achieve that, we really need to aim to use from the outset best-in-class digital engineering capability and practices that can enable and empower fast decision-making. And also, in line with this, traceability and enduring preservation of design options. And in doing so, we're going to be able to achieve game-change innovation, whilst also ensuring robust control of the project to mitigate any programmatic and technical risks as they come up. So we landed on 7 design principles that support this. And again, as I mentioned, these will really help to inform where the investment goes in terms of digital tooling, and how does the overarching kind of digital architecture look like. I won't spend too much time on this because I think Harriet will bring this out in the overview of some of the outputs. So with that in mind, I'll hand over to Harriet.
Sorry, Harriet, we can't
Sorry,
hear
can
you.
you hear me?
Yeah, that's
Yeah,
good.
you got me now. Oh, thank you. Sorry. Thanks, Sonia. Please can we move on to the next slide? Thank you. So over the course of the program, we used the program ambition, as Sonia's just mentioned, and the design principles to help us bring together two main outputs. So the first of these was the process catalogue, which was specific to the space-based solar needs, and brought together the capabilities and processes that are needed in the digital engineering space to allow the movement through the quick development cycles and have multiple simultaneous development cycles happening. We focused on the people, the process, the tools that would be required to achieve this. The second deliverable was the prioritized digital engineering roadmap. And this was split into 3 time-focused prioritization areas and cut across 4 different capabilities, focusing on the X-dimensional design management, the supply chain and manufacturing management, simulation and verification, and agile program management. It also touched on some of the key foundational capabilities that are required, such as data practice and communication and connectivity. I think everyone will agree that we've had some really interesting conversations over the 8 weeks, and all of these could have led to their own workshops. But it's been agreed that the initial priorities that need to be focused on are the implementation of a risk management tool, and how we can look at the digital capabilities that are required for complex project management, and also to focus on the requirements and assumptions management and the people, the process, the tools, and the data that will be required to implement this as we move into the concept design phase. So yeah, thank you very much, and we're really excited to see what happens next. So I'll hand back over to you, Frank.
Great. Thank you very much, Harriet and Sonia, for talking us through the digital engineering piece. John from Fraser Nash Consultancy is now going to talk about the standards and gap analysis work that they have done.
Yeah, brilliant. Good morning, everyone. Hopefully you can see my slides there.
Yeah, it's all good.
Yeah, brilliant. So yeah, my name is John Bull. I'm a senior engineer at Fraser Nash, and today I'm going to be talking about the standards landscape for space-based solar power. So I'll start off with a general comment on standardization. That is that standardization is useful where multiple organizations are tackling a general problem and require some level of interoperability or recognized safety. And the questions that we're addressing in this work are, what is the current standards landscape of space-based solar power? Where are the gaps? And then of those gaps, what are the high priority areas to standardize? In terms of our approach, we started by looking at the high-level standards before drilling down into some key technical areas. We had a research team consisting of our task engineers, and then they were supported by our subject matter experts at Fraser Nash. And we reviewed over 250 different standards, guides, and similar documents, and produced our report with our recommendations. So now onto the findings and what we had. So starting off with our high-level gaps, we looked at things like the business processes, life cycle, safety, interoperability, and these are all kind of application agnostic, and they kind of apply to various different industries. So there's good coverage here from the standards, with the exception of life cycle, where we've got some quite specific stuff for space-based solar power. So very specific design standards, and in particular decommissioning of such a system is going to be quite novel for SBSP. And that was quite a serious gap that we identified. Looking at our technologies, so in terms of wireless power transfer, this is a very novel technology area and correspondingly has very few standards. There were some standards around things like frequency allocation and safe exposure limits. And we explored different applications such as radar to kind of confirm that the extent of the gaps in this area. For power conversion, this is very well standardized, as you can imagine. Things like interface to the grid and supplying power is very well standardized. And the main gaps relate to the reception of wireless power in this area. Then we've got photovoltaics. There's a lot of standards around terrestrial PV and also concentrated PV on Earth, but spaceborne photovoltaics, in terms of concentrated photovoltaics, that's less well standardized. And that's kind of our main gap there. And then in-orbit service and assembly, a very novel area, so using robotics in space. We looked at 5 main areas here, so robotics, in-orbit assembly, autonomous systems, the use of AI, and also additive manufacturing. And we found, significant gaps around the sort of servicing of satellites in space, which, as you can imagine, that's not a typical operation to go back up to your satellite and do work on it. So yeah, gaps around there, the interfaces of robotics and also things like grippers and tools that you might use in space with the robotics. Now onto the recommendations. So a reminder of the question at the start, which is what are the high priority areas to standardize based on the gaps we've identified? And here, to determine priority, we've used a guiding criteria of what is the opportunity of standardization to reduce the level of development work needed. And from this, we identified 4 high priority areas. So first of all, disposal and decommissioning. As scrutiny and concern grows over things like space debris, we're going to have challenges with decommissioning a satellite of the magnitude that we've got here. And so an SBSP development program needs to engage with the efforts of standardization in this area to ensure that large satellites are accounted for. For wireless power transfer, as the technology matures, an SBSP program also needs to engage with this. I imagine, well, we kind of imagine that wireless power transfer is going to have applications far and wide, so outside of SBSP. So it's important to ensure that SBSP is considered as those things get standardized. In-orbit assembly, we think that standardization in this area can provide a path to quality assurance of in-orbit manufacturing techniques. However, that's caveated with other space sector stakeholders may not be as interested in this because it is quite specific to SBSP, but still important for an SBSP program to have that recognized certification. And then finally, rectenna design, and this is how we receive the power back on Earth. The key benefit of SBSP is the flexibility in deploying power to a range of locations, and therefore there needs to be some standardization in that interoperable sort of features on the rectenna design. And I'll just wrap this up by talking about the low priority areas. To reiterate, it's not a priority to standardize areas that are highly specific to SBSP. For an area to be standardized, it's got to have agreement and perceived benefit amongst a group of stakeholders. So things like in-orbit servicing, robotics, launch procedures, and space solar equipment are all gaps in standardization, but lower priority because they're quite specific to SBSP. And that concludes the standards landscape. So I'll pass over to Andy Bradford, I believe.
Thank you very much, John. And yeah, you're absolutely right. Andy from UK LSL will talk about the regulatory piece, which fits nicely with the standards. So over to you, Andy.
Thanks. Hopefully you can see my screen. Yeah, my name's Andy. I'm co-founder and CEO of UK LSL. We, amongst other things, including launch services, we look at regulation. We have been doing for a long time, spaceflight regulation. So we undertook this study to look at the regulatory aspects of SBSP. So just going to program objectives, study objectives. Again, it was a very technically focused study to look at the technical regulatory challenge that would be coming with the SBSP program as it's provided, and very much looking at the sort of roadmap that Frank put up a few minutes ago with these intermediate IOD missions. And really, just jump into the crux of this, was to keep regulatory issues off the critical path of the program and to make sure that we we had plans in place and we could put actions on the program, particularly with regulatory engagement and making sure that the regs were ready so that you could license these missions when you wanted to and you needed to. So obviously there are big challenges associated with the final configuration, which is 12, 13 years away. But actually some of the intermediate missions also pose some issues and some technical challenges, which actually John has kind of highlighted. You're going to hear a lot of commonality, and I assure you we didn't get to talk beforehand, so that's good that we've done two quite overlapping studies and come up with the same conclusion. So yeah, looked at these things and to come up with some recommendations and next steps basically. So that included looking at current and foreseen mission plans and technical solutions. So my background is spacecraft systems engineering. I've worked at SSTL and built quite a lot of spacecraft. I've been involved in a lot. So we're also aware of the regulations are, will and will not sort of allow. I mean, they're not prescriptive in terms of it's not that they will or won't allow, but we do know from how they're structured that if you're going to do a 2-year or 3-year development program like the early IOD mission, if it has certain features in it, it might be difficult to get that through the regulatory licensing process because, quite rightly, in the UK, at least, we're looking at mission robustness, not creating any debris, not having any liabilities, not basically flying satellites which have either a good chance of not working and or creating problems for other satellites. So that was the main sort of issue in the first, or the focus of the first piece of work, and to say, well, actually, we should probably make technical solutions that look like this. They will be most licensable. And then put a plan in for addressing those challenges. This includes inputs to those technical solutions and talking to the regulators. So main piece of our work actually was talking to the regulators and saying, well, we think this might be an issue here, sort of, do you agree? And then generating what we call this licensing roadmap, which I'll show you at the end of the presentation, which is a very, very top level plan, which shows the kinds of things that we think should be done and put into the overall program plan to make sure that you meet that objective of not having the regulatory stuff ending up on your critical path and ending up with a delay because you didn't think that putting something in place which you needed to get your licenses. So the main regulatory challenges, and this is interesting because it does overlap with what John just said, the whole area of wireless power transmission, both in terms of the space-to-space, so you may not know, but there's an early concept idea which is to do an in-orbit depot where you beam power basically between two spacecraft. But of course, the rest of it from the second demo and then all the way to the end is all about wireless power transmission from space to ground. This is not really it doesn't really fit, or is not really covered easily and readily with any current regulation. So there's bits of it that kind of fit in with certain regulations. Of course, it has relevance to spectrum and safety. And we saw, there is some work and there's some existing things here that people would look for. So, for instance, spectrum, and I think this is going to be covered elsewhere probably, you probably will need dedicated spectrum allocation. Spectrum is allocated every 4 years at the World Radio Conference by the OTU. It's a long process to get allocation, so you should have time, but you've got to get on with that early and start working on what spectrum you want. Safety, as well as, what are the safety aspects of this? The early work has shown that it should be safe, but there are regulations and there's some standards that we probably need to abide by, including these International Commission on Ionizing Radiation Protection, which is what Ofcom would look for in a license application, and also another one which is about control of electromagnetic field. So the second piece is again the large-scale autonomous assembly of structures. So we do this. We know how to do some of this in space. I've worked on some active debris removal missions, but this is at a scale which is way beyond anything that we can look at and say we could regulate at the moment. It does fall under this general rendezvous proximity operations and docking, that's what the D is. But it's a scale of complexity which is way beyond what we've got. So obviously we know that the UK policy for this is in development, should be ready this year. The key recommendation is to make sure it recognises that. So this is the regulatory roadmap. Again, it's basically a representation of programme actions we think should be done in order to make sure that they interact and sort of intercept with the various missions that we want to do, and make sure again that the work is done in a time frame that allows those missions to go ahead when we want them to do, and to do the things that we want them to do. So the key recommendations, actually, it's really about getting working groups together and getting stakeholders together to look at who's responsible for this, and particularly the wireless power transmission, and particularly the safety aspects, and make sure that everyone's in a room and saying, yes, we understand what we're trying to do here, and this is how it should be done, and here are the kind of principles and standards we should apply. Again, working groups on spectrum, I think that's probably well understood that needs to happen. And then we definitely need to make sure, I think, that what we see as needing to be regulated on the RPO side is built into this discussion and this policy stuff that's going on right now, to make sure that we basically future-proof those late emissions and make sure that the RPO policy covers them and what they're trying to do. And then really, again, it's the last one. I'll jump to the last one. And it's really to recommend that this regulatory roadmap is incorporated into that overall program plan to meet that key objective of keeping regulation and licensing off the roadmap, off the critical path for the program, which I don't think anyone would want to happen. And I think that's where I will stop talking and look forward to questions at the end.
Thank you very much, Andy. And so we're now going to change tack a little bit from our program assurance strand to our wireless power transmission strand. And first speaker is Mike Hontoir from Satellite Applications Catapult, who will be talking on behalf of Blue Bear Systems Research about the work that they have done.
Thank you, Frank. Yes, so addressing a question that Frank raised earlier, how can we increase confidence in wireless power transmission? And this is a precursor to some of those IOD missions that were highlighted just now by UK LSL. Move to the next slide. So as of 2023, the majority of proposed space-based solar power architectures rely on the use of microwaves for wireless power transmission, or wireless transmission and receipt of that power. And this is something that has and is still being pursued by several nations. But what we've highlighted is that the magnitude of this wireless power transmission and the distance, they're orders of magnitude apart from where we need to get to what's already being tested. And this particular project is trying to look at the opportunity of developing a test that can try and bridge that gap, will be the first part of that gap bridging. So the objective of this project was to look at the feasibility of an increased distance test. And this will be part of the phase 1 of the SEI roadmap that we shared earlier. This project starts from a need, and I represented the user in this particular project, as I said, giving this presentation on behalf of the supplier Blue Bear. So these were the needs that we started with. Not going to read word for word what's on the slides, but as I said, we're essentially looking at wanting to understand atmospheric attenuation, quantify the beam density, and to be able to plot the characteristics of a wireless power beam at specific distances from a transmitting antenna. As I said, the gap bridging is achieved by using increased distance, and we will cover those parameters now. So these are the constraining parameters that we provided as part of this project. The frequency is relevant for space-based solar power. The beam intensity is designed to be at the higher end of what is currently allowable, and the transmission distance is not necessarily arbitrarily chosen, but it sits within that gap between what has already been done in hundreds of meters towards thousands of kilometers that we need to achieve. I will run through the concept of operations just to kind of give a flavor as what the test would involve. So the setup shown on the screen, as you said, there's a caveat at the top. The visualization is not intended to be completely representative of any particular solution. Essentially, at a suitable test range, we would have a transmitting antenna pointing vertically. The equipment involved would also require a high altitude platform, and commissioning and ground testing would be done before the test phase as part of this deployment phase. Once we have an airborne high altitude platform, it would then move into an intermediate altitude. So this is shown at 500 meters on this graphic, above the transmitting antenna, and it would then follow a predefined route to capture data regarding the intensity of the beam, and it would be able to plot this against its position in 3-axis so that we could understand what the intensity is and create beam characteristic mapping from that. This area, so the diameter of this particular area, is linked to the specific frequency, whether we choose to use amplification, and also the distance between the transmitting antenna on the ground and the altitude itself. So the distance is not explicitly given here, but there is definitive linking. And as I said, we set the upper and lower bounds for this project at the outset. The next phase of the test would see the altitude increased. This would enable us to understand any atmospheric attenuation effects, and we would conclude with the high altitude platform being recovered. So Blue Bear Systems Research identified 3 different types of high altitude platform. So this is an area that they do have specialism in, and we're going to run through very quickly these 3 different types of platform. So the first is a fixed wing UAV. So this scores highly for endurance and the ability to follow the required flight patterns, but it does score lowly for its inability to integrate well with large payloads, or payloads with a large surface area. And this project was looking at exploring whether it was possible to use a larger sort of multi-element receiving antenna as a payload, and we will come on to whether we think that is suitable in a moment. So aerodynamically, the fixed wing UAV is assessed as not overly suitable for this, and there's a rough order of magnitude cost for purchasing of a platform shown here. Second option is a rotary wing UAV, which scores highly in similar areas as the fixed wing, so for flight patterns, and it's got a very good sort of repertoire of operational experience, but it does score lowly for endurance and also for integration with large area payloads. And the final platform type, which was identified as an aerostat, does have different variants, which is why there is a varying rough order of magnitude cost. Scores highly for payload integration, but lowly for positional control and also autonomous control. And we'll come on to why autonomous control will be quite useful now. Essentially, one of the main points of the report that was generated by Blue Bear's work that they've identified is that we really do have to consider the environment in which these platforms will be operating. If we're transiting an area of high RF, then actually the flight systems within those aircraft will have to have RF shielded enclosures, and also it's likely that they'll go through they'll experience deadening, in which case, as I said, the aircraft systems themselves are likely to have to be autonomous so that they can work remotely and autonomously without the use of constant communication. Demonstration sites, this was one of the final pieces of work that Blue Bear did, identifying suitable demonstration sites. Because of the type of work that we're doing, they would have to be either a temporary danger area or a danger area. Given the timescale in which we were asking them to work, they've identified that it would need to be a danger area that's already established, and they've shown here that there are options available for the altitudes that we're looking for, and they are suitable in 2 of the cases for all of the 3 different types of high altitude platform. So the outcome of the report was that the first option is that we could go with a commercially available off-the-shelf rotary wing UAV, which would require some platform modification for RF shielding and additional enclosures. We could integrate that with a payload, but it would come with some constraints on payload sizing due to the aerodynamic considerations and downwash from the UAV. And inclusive of hardening, testing, commissioning, etc., a rough order of magnitude cost is £1 million at this time. What they've identified is that using a smaller product, reducing the size of the payload, reduces complexity and the necessary integration, and this would have a rough order of magnitude cost approximately half of option 1, and option 2 is shown here. So again, this is taking a slightly alternative approach, not using a multi-antenna receiving array, but using a single antenna, and the results would be that this trial would require additional passes to gain the same level of data capture, but by reducing payload platform associated facilities, it could come with a massively reduced cost. And that concludes my part of the presentation. Back to you, Frank.
Great, thank you very much, Mike. We're now going to go into modeling of space and solar power and wireless power transmission antennas. I've got 2 talks on modeling, one from Altair, and then after that, one from Lythene Electromagnetics. So, Swapnil, do you want to talk about the work that you've done at Altair?
Yes, thank you. Let me share my screen, Frank. Okay, all good. Can you see my screen?
Yep, we can see that.
Yep, thank you. Just sorting some of the stuff. So, good morning, everyone. I'm Swapnil Kulkarni, representing Altair Engineering. So today I'm going to present work done with Frank and his team on the antenna array and interference analysis. This is specifically looking into the modeling aspect, investigating the challenges. And okay, so let's roll on. So I represent Altair Engineering. I work as a principal application engineer. My background is computational electromagnetics, and we had primarily used Altair FICO, which is a comprehensive electromagnetic code, and WRAP, which is a more of propagation and network planning kind of tool, but specifically the satellite module from WRAP to investigate the interference on the site. We work on a pretty broad spectrum and portfolio, and we have an in-house consultancy team here in UK. Let's move on to the work. So we started with investigating the individual elements of the array antenna. So by this time, probably you might have seen a couple of images shared on the actual full structure of the SBSP. And it does has I want to recall a specific image wherein you have the antenna at the center and the solar panels at the top and bottom end, which collects this energy. And then you need a very key element, the antenna array, which then transmits this energy down to the receiver station, which would be a rectangle on the Earth surface at desired location. So we started investigating with the basic element, and this data came from Frank and his team. And so essentially you now look at the magnitude and phase for a tripole dipole arrangement, and you want to check how the steering works for 3 different configurations: 0 degree, 45, and 90 degree. So what you're looking now is at the just the individual tripole element I'm talking, wherein it has been modeled with in the tool FICO, which is considering the dipole as a very idealistic dipole, the ideal dipole elements, where you are looking at infinitely small dipole. And then you look at the radiation pattern in at azimuth for 0 degree, 45, and then 90 degrees. So obviously the blue corresponds to the ideal dipole, the red corresponds to the dipole, which is now a more realistic and has an impedance match. And then you're looking at the green one, which is with the Lycian EM. There's a comparison, how do we stand against? Okay, so you can see a pretty close match. with the red ones, yes, there's subtle difference, obviously, because you are now looking at realistic dipoles, and there will be coupling in between this each of the individual dipole antennas. Now, if you observe carefully, it doesn't matter for 0 degree or 45 degree. So there is a mutual coupling effect, which has a very dominant effect on each of the other elements, and the impedance which the individual antenna is looking now changes, and then this obviously leads to a kind of a more directed lobe, or you can say more directive pattern in a certain direction compared to other. This can be also investigated if you look at just the currents on the individual dipoles, or just looking at the near field, which is very obvious. So yes, you will need to think of working on how do you offset this magnitude and phase in order to achieve the directivity and steering at a very as per the design specifications. Let's look at the model one. Now what you are looking here is the full, so that's for the image I have recall from the space-based solar power typical configuration. What you are looking is, this is not the final array, of course, but it's a 3D, and you can see it's a twisted arrangement. Each of the tripole dipole is now arranged in a specific XYZ location, having its own individual phase and magnitude. This again came from Frank and his team from CSA, Catapult Space Application. So in FICO, we had a customized macro where all it does, it just reads the locations. You have the base antenna element. It could be anything. In our case, it was specifically this tripole, which we investigated. And then the same base dipole element is then used to generate an array. And you could see this is a 21 by 60 arrangement. And we then quickly ran this model to investigate how does the far field pattern looks for azimuth, and then in elevation for a dipole element, which was considered as a full wave dipole with a match impedance. And then you could see there are two curves, each for azimuth and elevation plots. Essentially, you are looking at the gain of the antenna, or how the far field pattern would look in a 2D in the azimuth horizontal plane, and elevation, the vertical plane, at 0 degrees, 45 degrees, and 90 degrees. And of course, a comparison with the Lyson EM code, how does it stand with respect to. So the difference here is we are now using a full dipole, or a physical structure of the dipole elements, and then of course, how does it stand with the ideal. Now, what we then decided to in the next stage was to build a more larger array, or there was a catch or caveat. So the for a larger array, when we started to do the actual physical modeling, it was quite big, and probably took, so I did allow to run, and it takes literally 3.5, close to 4 days, I would say, to build the complete array. Now, bear in mind the fact, the size and the number of elements. So the model one previously I presented, that has close to 3,780 dipoles. So what we did was a quick investigation. Can we split this array? And this we had investigated. There was some work done in the past, and very happy to say that we have been involved with one of the Japanese laboratory previously on similar kind of project. So we decided to split the previous array as a validation to come out of a more, I would say, intelligent strategy, because you are now looking, the actual full size array has a much more higher number of elements, probably million array elements. And then the wise strategy is then split the array into 4, or we were investigating, should we split into 3 or 4 parts? So you split the large array, the previous one, model one, into 4 parts, and then you solve individually, and you now extract the far field pattern and combine only the far field pattern, which is a more lighter model, and then you solve. So there was a validation done quickly to understand how does the far field antenna or the far field patterns of the array compares to the antenna pattern when the array was split into 4 subsections or 4 parts. You can see there's a quite close match, and this we even just investigated for 0 degree, what I'm presenting. Of course, we did investigate for 45 and 90 degree. Now, obviously, this approach once was validated, and we are quite okay with the results for different 45, 0, and 90 degree steering. We then move to the model 2, which is much larger. You can see the model 2 now contains close to, you can see the number of, now this has kind of a 3,690 dipole for each of the subsection, and the total number of dipoles are now close to 14.5 or 14,760 precisely, the number of dipoles in the entire array. So obviously this approach is much feasible, because if you split it individually, it just takes probably close to 35-40 minutes to build the array, the physical model, and then you can solve this in 6 minutes and 8 cores. The memory requirement is very, very, very negligible. This was, the models were run on a pretty standard machines. So there was a learning experience, yes, that you need, which we have feedback to the developer team here in Altair, that accelerate the model build process for, I would say, very large antenna array kind of modeling stuff. So let's move on to the next stage. So you are now looking at the, again, how does the far field pattern in azimuth and elevation looks for 45-degree steering configuration, 90-degree steering configuration, and 0, 45, and 90-degree, both in azimuth and then elevation. Again, this has to be compared because, of course, we were at this stage, we're not validating against measurements. So it would be good to compare against something on the other code, which in this case was the Lycian EM, which I think my colleague or friend would talk later. So once we are happy with this, we are now moving to the next stage, which involves interference analysis. Now that we had worked on the 2 different model variants, decided to use the larger array configuration, and the far field pattern from Lycian EM was used in this case. So WRAP is a tool which can investigate the interference between existing satellite networks, or interference between your space service and terrestrial service, or probably interference from space to terrestrial stations. Or if you want to investigate what if there is a flight trajectory or path, and then you have a satellite, and how, in this case, because you are transmitting, these are the specification of the transmitter. You can look at the transmit power, and then of course we use WRAP to quickly model the transmit antenna. You can define the location. Of course, it's a stationary, this is what the distance, and you have the receiver antenna, which is rectina at a certain position. So these were the specification shared to us by CSA. And then what we do was we use WRAP, which is our in-house tool. WRAP has been in the market for quite long, and it's very popular in the defense and aerospace domain, specifically on the radar optimization, a lot of satellite communication, and those kind of simulation. Don't not go in detail. So what we are looking now is you need to specify the antenna specification for the transmitter, and then the receiver antenna, which was defined in a specific location here in this case. So we have a specific built-in map data. In this case, we use the map data from Ordnance Survey, which is local to UK, and it has a reasonable good, I would say, accuracy. You can change the resolution in this case. So we are now looking at the intentional, so where we have defined the rectina specification on the Earth station at a certain UK location. Don't want to disclose, but you can easily look. The good thing is you can directly define the national grid coordinates, and it's identify where exactly the location is. The first approach is obviously we want to first run a basic analysis and check what is the coverage analysis, or what is the power flux density received at a specific location where the rectina is located on the Earth surface. Bear in mind the fact we are taking into account all kind of aspects: reflection, diffraction, scattering, and attenuation. Because we are including the map data, it also includes the terrain profile, yes. And WRAP, as I said, has been in market for 3 decades plus. We consider all the ITU attenuation model, atmospheric attenuation. You can there's a very specific space, I think, propagation ITU models which are implemented in WRAP that can take care the path loss, and that's specific the signal loss when it comes down from say 35,000, 36,000, or we support various LEO, MEO, and GEO orbits, but in this case it was very specific. You can calculate a lot of other aspects, but the first analysis is look at the power flux density when it comes typically to satellite, when you want to check the received. The next approach is interference. As I said, you can investigate different interference scenario. I'm just presenting one of those. So you have a test space. This is where your integrated this rectina station is, and we added another test-based station to understand what is the interference if it is at a certain vicinity. And so obviously we define the specification for the test-based station, which is in vicinity to the receiver or rectina. And this is where it is located on. And then, of course, when you run the interference analysis, you can look in a very, I would say, high-level sense, what if the satellite is acting as an interferer, and vice versa, if there are other ways, if the rectina ground station is now referred as an interferer. Okay, you can reverse back because it's a simulation, and there are different approaches. So obviously, when satellite is acting as an interferer, you can look, wow, there are some desired and undesired effects which you can observe. There's also an unwanted effects, which is obviously what we are really intended to look at the test-based station. So you can check what is the amount of power, the frequency. There are a lot of other aspects you can look into, intermodulation effects, and can you add filtering characteristics and other stuff. Not going detail, but obviously I would primarily look at the signal to noise ratio to begin with. And then on the other side, you can check how does, in the sense, the rectina is acting as is now is treated more as interfered. So it impacts both the satellite and the test base station. And obviously, due to the proximity of test base station, in this case, there will be some interference on the ground station. That's relatively low compared to satellite signal, but yes, that's pretty much from me. Thank you very much.
Great, thank you, Swapnil.
I'll stop sharing my screen. Yep.
Right, so
Thanks, Frank.
We'll hear from Timothy, who has done the work with Lycene EM.
Yeah, I just need to wait for Swapnil to stop sharing so I can share.
Yep. Sorry, Tim. It was
Quite right.
Yep.
So while Timothy is loading it up, I just want to acknowledge the support from IECL that we've got during these projects to help us with Cassiopeia as well. So Timothy, all yours.
Right, good morning. My name's Dr. Timothy Pelham. I've been contributing to this work through Lycene EM Consulting. Just to give a little bit of brief introduction, Lycene EM is an open source electromagnetics package, which I published in April last year. It was originally intended for rapid virtual prototyping of antenna arrays for complex systems, whether it's a mobile base station to go in an urban built environment, or a radar to go on a satellite, or indeed medical imaging. The idea being to allow for rapid collaboration and flexible modeling of what can be very complex scenarios to allow for the design and de-risking of different antenna array designs. It's since developed a little bit more into a much more capable channel model with both frequency and time domain modes. And we've published some quite good research validating it at quite high frequencies, up to about 24 gigahertz, where it's demonstrated an agreement between the measurement and the modeling of about -69 dBs RMS error. It currently uses a Huygens approximation instead of using full antenna array design information, but that's intended to allow for this rapid virtual prototyping approach. So in terms of the actual space-based solar power, for this initial work, we had a look at Cassiopeia at different scales of operation. Swapnil's already showed some of the comparisons between FECO's both ideal current source antenna sources and much more realistic antenna sources with much more significant coupling between the different elements. And I think that that is really the key thing to look at as we develop the software solutions and the designs for wireless power transfer over these distances, is the beamforming and the antenna array design support that robust and easily controllable wireless power transfer. Just to give you a bit of an idea of the scale of the problem, the largest antenna array that we modeled in part of the initial work, that's what we introduced in Model 2, has almost 15,000 elements. And within Lycene EM, it builds and simulates in less than 2 minutes, which is excellent. But even on this graph here, on the right-hand corner, you can see a 2D cut in azimuth of Cassiopeia at this scale, steered to 0 at 60 and 120 degrees. And you can see it has this quite good directivity in the desired directions, but there's also a lot of relatively high side loads, which is not desirable for efficient wireless power transfer. And also, this is only a small fraction of the full-scale Cassiopeia, or indeed any of the current space-based solar power concepts for transferring power over this distance. The full scale is just over 1.7 kilometers across, with over 1 billion elements. That's 3 to 4 orders of magnitude larger than the largest antenna array ever built on Earth so far. So there is an awful lot of ground to cover when it comes to scaling up antenna arrays, and also the design work and the modeling software to support these kind of scales of use. And more importantly, it's also a case that as we scale up, we've got to be able to support a traceable process, so that multiple different entities can use the same model and use the same information to be able to predict and understand the areas in which these power transfers will be ongoing, and the effects across the landscape around the receiving array, and also the effects of interference and things like that. And that's something that we're going to be looking at in the next year or so. Lycene EM, which is, as I said, open, so anybody can use it and access it and contribute to its development. We're going to be looking at open standards for antennas and array patterns, antenna array design, and also for wireless power transfer, with the intention being that not just for space-based solar power, but also across mobile comms, satellite communications, and radar modeling and design, there is this opportunity for collaboration and contribution as we scale up to the computational intensity required for space-based solar power. And that's not just in terms of standalone modeling on high-performance computing clusters, but also enabling much more accurate modeling of the atmosphere and the effects of different weather conditions on wireless power beaming, also on the ability of different researchers across the globe to do initial modeling to investigate the effects of different beamforming algorithms on the wireless power transfer as a whole. And that is, I think, something that's going to be very interesting as the research develops, as we move from large, but not large enough for the scales required, to being able to support these gigascale antenna arrays at both ends and having robust and flexible models that we can transfer and demonstrate the safety and the reliability of this technology. Just in case you have interest in research or collaboration in this area, I would also like to take a minute to mention that the workshop that we're going to be holding in Bristol next week on the 4th of May, we have speakers from the UK Space Agency, European Space Agency, and also Professor Paul Monks, the Chief Scientific Advisor for the Department for Energy Security and Net Zero. And if you're interested in this particular area, or if you are looking to get into space-based solar power, I would encourage you to register for a ticket and come along, and we can have a good discussion on the key enabling technologies, but also where to go from here and what things we need to include in these open standards.
Great, thank you very much, Timothy. And we're now going to a different topic again, and Jeremy is going to talk about robotics.
Thanks, Frank, and I hope you can hear me and see the screen. Good, excellent. Good morning, everybody. My name is Jeremy Haddell. I'm the In-Orbit Service and Manufacturing Robotics Development Lead for the Catapult, and I led the team looking at Work Package 4, which is the Midas tooling interface proof of concept. What does Midas tooling interface mean? Well, as has been, my slides will move. There we go. As been alluding to earlier, we're going to have to rethink how we design spacecraft, particularly when we start to think about space-based solar power. But this has a lot of commonality with the way we construct spacecraft in the future for in-orbit servicing, deep space exploration, planetary exploration, all kinds of different things. And what you see here is some of the key areas we've been investigating around the design of future spacecraft, and the ones highlighted in yellow are the ones that we've really focused on in this program. And we're looking here at things that are modular. That's going to enable us to build them faster and more effectively, and potentially without the need for astronaut EVA in the process. We're going to need some sort of grapple fixtures, some interface standards, a way of quickly disconnecting and attaching devices, tools, parts of the spacecraft. And we also need to start thinking about true life design for robotics. It's okay to start to think about using robotics to design and to assemble, the spacecraft. But we also need to think about how we're going to service that spacecraft. How do we repair solar panels? How do we repair parts of the spacecraft as they will do in the space environment? Now, a lot of people have been putting a lot of effort into looking at how we dock spacecraft together. But what we saw is there's not a lot of effort being done in the attaching the tools to robotics. And when we started looking into this, we saw that, yes, the Canadarm has interfaces on it that allow us to attach various different tools. But just because of the nature of the Canadarm, it's quite a complex and large device. But when we start looking in traditional manufacturing environments, we see the kind of devices you see on the right of the screen there, which is a standard tool changer. Now, these are being applied to industrial robots for decades and allow industrial robots to carry out a range of different tasks without having to change the robot. They're modular, they're quick release, they give all the kind of things that we think we might need to assemble and service something like a Cassiopeia spacecraft, because we don't really know what that looks like yet. So we're having to make some assumptions around what we need here. So the picture on the right is essentially what we focused on. And what we came up with, sorry, let's just talk about deliverables. We wanted to develop a validated proof of concept. And we needed to have a digital twin of that because, again, we want to be able to manipulate it, we want to be able to use it, and we don't have enough data yet to say this is the actual design. And we wanted to create a reference document. And that document is not the final article. It's trying to gather data together or information together for the use of the tooling interface and how it can be designed. And we expect it to be built on and expanded as we go along and we start to understand how the spacecraft is developed. So this is Midas. This is the mechanical interchange device with interface standardization. We're quite good at coming up with clever little names for things, but essentially Midas consists of two components. The upper component is be affectionately called the baked bean can, and a lower component which is called the coaster. And these look a little bit like this. So the baked bean can on the left-hand side is the main interface to the robot. It's on the previous slide we've shown it attached to a universal robot. That's not a robot that you would send into space, but it's been designed so that the bottom end could be changed and you could attach it to essentially any type of robot that you might want to use in orbit. That could be a traditional serial arm robot, or it could be a crawler robot, it could be a soft robotics device. It doesn't really matter what it is. The aim of this would be able to build this, to attach this to any type of robot manipulator. On the upper face, you can see there you've got some guide pins. Those guide pins interface with the coaster, which you can see on the right-hand side. Once they're locked, they've come together as a single unit. There's a mechanism inside the main body of the canister, sorry, the tin can, that locks the two end devices together. So you can see there are some slots put into the guide rails inside the can, which you can't see. There is a mechanism that locks those in place. It's not overly clear on this picture, but there's a ring of pogo pins in the middle that provides us power and communication interface to whatever device is attached to the coaster. Now, the coaster itself is a fairly dumb device. It has no onboard power, no onboard computing. It receives all of that from the can. But what the clever thing about the coaster is you can attach any different type of tool on the end. So on the right-hand side, you can see we've got a fairly simple 3D printed gripper, but that could be a camera system, that could be a much more sophisticated gripping mechanism. It doesn't, the principle behind this is what you attach on the end of the coaster is really up to you, but all the power and the control comes through the main robot system and through the beam, the tin can onto the coaster. So those are the components. I know we're a little bit behind on time, so I was going to show you a video of it working, but I don't think we've got time for that. Instead, I'll show you what the digital twin model of it. So we modeled this digitally for a number of reasons. One is it gives us a great video that I can show you today, but also gives us an idea of how we can operate this device in the space environment. Now, this is operating our test facility, and this is a model of our test facility. But ultimately, what we're going to be able to do is replace the background images with real CAD data, or if we have visual data from in situ, so if we've actually built a spacecraft, put it into orbit, and I've got the data, I can then overlay that data into the model and see how the robots are interacting with that real spacecraft. I can also do this now with augmented reality or virtual reality, so I can interact directly with devices. And that's the real power of this digital model of the equipment. As I say, we also created a reference document. The idea behind this reference document is not to be a fixed and hard document that tells you what you must do to operate with a Midas device. It's really about capturing the requirements and the assumed requirements, providing some traceability for those requirements, setting out the future needs for the development of that interface. So beyond the proof of concept and how we develop that into something that we can use longer term as the spacecraft develops. So that was a quick whistle tour of what we've done on Midas, and happy to answer questions later.
Great, thank you very much, Jeremy. We're now going to go to our last theme of the day, which is infrastructure and security. And we're going to start with James from CGI talking about mission security and mission security analysis.
Cool, thank you, Frank. Let me just bring this up. Maybe you can still see the full screen. So yes, I am James Hedges. I am the business analysis lead at CGI for anything to do with space-based solar power. I'm just going to give you a very quick overview of some work we facilitated around cybersecurity for SBSP. So the need for cybersecurity in space-based solar power is really just an extension of the need for cybersecurity in space. With our lives being so intrinsically linked to space and with it being regarded as one of the 5 warfighting domains, we have to assume that nefarious actors will look to perform nefarious actions in, through, or from space. So with space-based solar power, we have a pretty unique coupling, which is that this is an energy project in space. So with both energy and space being designated as CNI in the UK, and unfortunately, as we've seen in the last year or so, some nations considering civilian energy infrastructure to be legitimate military targets, the need to protect and secure a space-based solar power capability is pretty self-explanatory. So CGI were contracted to deliver 2 initial cybersecurity work packages in support of a wider series of space-based solar power cybersecurity analysis. These were ultimately tasked with delivering an initial space-based solar power cybersecurity plan and an initial space-based solar power cybersecurity analysis. So to complete the security analysis, we hosted a series of workshops which involved a number of experts and contributors from across the space energy fields. You can see from the logos there, some of whom are also presenting here today, and I'm sure many others are in the audience. So we had 3 workshops over the course of about a month. We used them firstly to scope out our deliverables, so what's going to be in the plan and the analysis, what they need to look like. Then workshop 2, which was really getting into the sort of bulk of things and identifying and discussing security threats and risks to space-based solar power. And then finally, we used workshop 3 to review those risks and threats, and then to combine them with research and start to talk about the scoring that we'd apply to them. So we took a threat-led approach to risk identification. So that involved firstly considering what a cyber threat to space-based solar power might be, what kind of person or group might pose such a threat. So that is the threat actor. Then we identified vulnerabilities in the system, and given that the space-based solar power capability is in a conceptual phase still, we had to be pretty clear with the assumptions that we were making to sort of identify what those vulnerabilities might be. But once we got those and we can combine them with the threats, then we can derive risks from that. So over the course of this analysis, we identified 24 potential threats, which exploited 15 highlighted vulnerabilities and led to a derivation of 27 distinct risks. Of those risks, we classified 5 of them as high risk, 19 of them as medium risk, and 3 of them as low risk. And you can see on the screen, I've put the 5 high risk risks on the screen. And these clearly demand the most attention to sort of prevent and mitigate. You can see just from that table that the majority of them revolve around loss of command and control, and generally not receiving power at the intended power site. It's really important to clarify here that we did not attempt to identify controls or mitigations at this stage. So the scores you're seeing here represent the unmitigated risk. This is just the first draft of a security analysis. It will need to be an iterative document that lives and grows as the project and capability itself grows. And as we detailed in the recommendations of the report, controls and mitigations will need to be identified as more risks and more threats are identified and analysed. So as mentioned at the beginning, we delivered a draft mission security analysis and a draft mission security plan. The analysis, as you've seen, contains mostly the identification of threats, risks, and vulnerabilities, whilst the plan is a comprehensive document on establishing a good security culture, applying relevant standards and frameworks, complying with relevant laws and regulations, and then looking at the interdependencies between cybersecurity and physical security and personnel security. In terms of next steps for both the plan and the analysis, which live together, we'll need to do an asset identification activity, so understanding what are the assets that we are including in the space-based solar power capability so that we can properly protect them. We'll need to identify a governance structure that will oversee security, ensure that it's baked in at all stages. And as I've mentioned, we'll need to iterate the security analysis. So what we've done essentially so far is that initial analysis. As I mentioned, controls and mitigations will have to be identified. That should then feed in the next iteration of a design. And then following that, there'll need to be another security analysis done on the new design. So essentially, as one thing progresses, the security analysis will then have to be updated to reflect that. So that, as I said, is a very quick overview of what we've done so far in cybersecurity for space-based solar power. I'm happy to take any questions at the end. Thank you.
Great, thank you very much, James. And then last but not least, we've got Richard to talk about the biodiversity assessment. So Richard, before you start, looking like the time won't allow us for live questions, so I encourage everyone to type their questions in the Q&A box, and also for the other panelists to look at those questions and try to type an answer. Over to you, Richard.
Okay, thanks very much. Just share my screen. I think that's correct. Frank, can you confirm that's visible?
Yep, that is visible. Thank you.
Okay, thanks very much. Right, my name's Richard Arnold, and I'm an ecologist working for SLR Consulting. We've been looking at the potential effects, both positive and negative, of the REC tenor on wildlife habitats and species or biodiversity. The REC tenor will resemble a mesh suspended above and parallel to the Earth's surface, and it will cover a large area, up to about 62 kilometers squared, or a diameter of about 9 kilometers across. Associated with the REC tenor will be electrical cables and other ground-based infrastructure. As the project is at an early feasibility stage, the location, timescales, and much of the design and construction details are not yet known. For example, the REC tenor could be on land or at sea. So we've been looking at both scenarios, a REC tenor based on land or a REC tenor based at sea. In both cases, the planning and development is highly regulated, including strong protection for wildlife and habitats. The effects of the REC tenor on biodiversity will therefore need to be assessed under the environmental impact assessment regulations and habitats regulations, and care and time will be needed to navigate through these and achieve a planning consent. For example, it will need to be demonstrated that there will be no adverse effects on any wildlife sites protected by law. On the slide, you can see just an illustration of how many of them there are and how they're distributed around the UK. The project will also need to follow the mitigation hierarchy and demonstrate a net gain for biodiversity. That means that negative effects should be first avoided, and those which cannot be avoided should be reduced as much as possible. And finally, any residual impacts should be fully compensated. And after that, even further, additional measures will be needed to capture, needed to achieve an overall increase in biodiversity at or near the project site. Dealing with avoidance first, the main way in which this can be achieved is by locating the REC tenor in an area of low biodiversity, supporting only widespread habitats and species. On land, this is likely to mean locating the REC tenor in an area used for intensive agriculture, such as arable or pasture. And at sea, this is likely to mean locating the REC tenor away from the coast in shallow seas and away from more unusual habitats such as reefs and sandbanks. The routes for electrical cables and other infrastructure would also need to be carefully chosen to avoid impacts wherever possible. Once an emerging location is known, detailed ecological surveys will be required to establish the likely effects and inform further mitigation measures. The survey standards and methods will be aligned to new wind farms or similar types of infrastructure. Surveys will include birds, bats, mammals on land and at sea. The slide is just some nice images of the kind of animals that we would need to consider as part of our survey work. Mitigation measures will be needed during the design, construction, operation, decommissioning of the REC tenor. Such measures could include ensuring that the microwave beam is too weak to be harmful to wildlife, such as birds which may fly through it or land on the REC tenor. Positioning the REC tenor at a height where most wildlife would not encounter it, for example, above the height that deer could jump, and also the height that dolphins, for example, could jump, which is much more complicated than it sounds. Designing the REC tenor to allow light through to the ground or sea for photosynthesis, while at the same time being detectable by birds and bats, would also need to be included in the mitigation, as would designing the REC tenor to minimize the risk that birds and bats could become entangled in it, even if they're flying at high speed. Some species of birds, for example, dive into the sea to catch fish. Another measure would be reducing the number of poles required to support the REC tenor, if this also had the effect of reducing its overall footprint. And then managing the construction, maintenance and decommissioning process carefully to minimize pollution and disturbance of wildlife would also be important. This could include reducing underwater noise during the installation of the REC tenor, because that could disturb marine mammals. And that would all be similar to what's done now for offshore, on and offshore wind farms, for example. Even with these measures in place, there is potential for profound changes in the ecosystem below and around the REC tenor. On land, this would be through loss of tall trees, potentially, reduction of agriculture, exclusion of some large birds and some species of bat, and increase of shade. And at sea, this could include the introduction of hard surfaces, so that attracts different species to live in the area which don't live there now. Reduction in fishing, exclusion of plunge diving birds, and marine mammals, increased shade again, and changes in marine processes around the REC tenor poles. To finish on a positive note though, the reduction in human agriculture and fishing, if that's what happens in and around the REC tenor, could be a significant benefit, creating a de facto protected area and offsetting the potential negative effects on biodiversity of the REC tenor and the other infrastructure. This is very much like everybody else, a preliminary assessment, and much more research is needed to properly understand the effects of the REC tenor and how best to mitigate the negative effects through careful design, and also how best to maximize the benefits that could be delivered in the way I've just described. And that's my 5 minutes on what the work that we've done so far on biodiversity impact. Thank you, Frank.
Fantastic. Thank you very much, Richard. What a great way to end with pictures of animals.
Yeah.
I'm afraid we've run out of time for any live Q&A, but maybe if I can invite all the speakers to put their cameras on briefly. I just want to say a huge thank you to all of you for your time and effort this morning and throughout the program. Thank you very much, everyone, for attending as well, for dialing in and listening to our talks. There have been a few questions around making slides available. We'll make our best efforts on that. We're acknowledging that everyone presenting needs to agree to share those as well, but we'll work on that. So yeah, just a close-out comment. Thank you very much, everyone. You'll see this is the start of a journey where we've engaged a small number of organizations to try and work towards space-based solar power and realizing space-based solar power, but inevitably it will require the whole supply chain and a much bigger collaboration to deliver this going forward. So any other questions that remain in the chat or on the Q&A, we will pick up afterwards as well. So if you've got any last minute questions, please put them in the Q&A and we will make sure that they get answered. So yeah, thank you very much, everyone, and hope you have a great rest of your day.
Thank you.
Thank you.
Thank you, Frank and everyone. Thank you.